Welcome to this deep dive.
Low.
Today, we're tackling something that affects millions. We've got a bunch of articles, some research here, all focused on shellfish allergies.
Right. A really common issue.
Yeah, and our goal, our sort of mission is to figure out why. Why are these specific foods, shrimp, crab, lobster, clams, why are they such potent allergens?
That's a great question. Because the sources are pretty clear. This is the #1 food allergy for adults in the U.S. We're talking, what, about 3%?
Around that, yeah. And it's not just common, it can be incredibly severe,
Yeah.
life-threatening even, from just a tiny bit.
hmm
Someone used the phrase culinary Russian roulette, and it kind of stuck with me.
That captures the anxiety, definitely.
Mhm.
And, the core thing we need to grasp,
Mm.
which the sources hammer home,
Mhm.
is that it isn't a poison or a toxin in the shellfish itself.
Right. It's not like eating something spoiled.
No, it's the body's own immune system going haywire over a specific protein. That's the real mystery here.
Okay, let's dive into that then. So forget the idea the shellfish is inherently bad, it's about the reaction.
Exactly. Think about your immune system, right? It's this amazing defense network, always looking for invaders, bacteria, viruses, that sort of thing.
Using things like antibodies as like little identification tags.
Precisely. Highly specific tags looking for trouble. But in an allergy, the system makes a mistake, a really big one sometimes.
It misidentifies something harmless, like a protein in food, as a dangerous enemy.
It launches a full-blown attack.
Yeah.
The sources describe it almost like, friendly fire inside your own body.
And with shellfish, the main target, the protein that causes all this fuss, is called tropomyosin.
That's the one, tropomyosin. And what's interesting is it's a really fundamental protein. It helps muscles contract.
Because it's in lots of animals.
Oh, yeah. Crustaceans, shrimp, crab, lobster, and mollusks, too. Your clams, oysters, scallops, mussels. It's a core muscle protein.
Wait, so this basic building block of muscle, something found everywhere, even in us probably, that's the trigger.
In shellfish, yes.
Okay, so why? Why the shellfish version? Did the sources get into what makes that tropomyosin so problematic?
They did. They point to a couple of key properties. A big one is just how stable it is.
Stable, like tough.
Really tough. Cooking doesn't easily break it down. Boiling, frying, steaming.
Yeah.
The sources say the heat barely touches it, structurally speaking. And it also tends to resist being broken down by your stomach acids during digestion.
Ah, so it actually reaches the immune system pretty much whole, intact, ready to be flagged.
You got it. Unlike lots of other food proteins that might get denatured by heat or chopped up by digestion, tropomyosin often gets through the gauntlet relatively unchanged.
Okay, that makes sense. It presents itself clearly to the immune system. What else?
The other major factor the sources highlight is cross-reactivity,
Meaning?
meaning the tropomyosin structure is remarkably similar across all these different kinds of shellfish. Shrimp tropomyosin looks a lot like crab tropomyosin, which looks a lot like lobster tropomyosin, and even quite similar to clam or mussel tropomyosin.
Ah, okay, so that's why if you react to shrimp, doctors usually say avoid all shellfish.
Exactly. Your immune system sees the protein in, say, a crab, and basically thinks, hey, I know you, you're that shrimp threat.
Yeah.
It can't easily tell them apart.
So it treats them all as the same danger.
Right. And this similarity is a huge reason why avoiding it is so critical, and why reactions can happen with different types. And interestingly, some research suggests that maybe even exposure to similar proteins elsewhere, like in dust mites.
Dust mites, really?
Yeah, they also contain a form of tropomyosin. It's possible, the thinking goes, that exposure to that might sort of prime the immune system, making it more sensitive, more likely to react strongly when it encounters shellfish tropomyosin later on.
Wow. Okay, so you've got this super stable protein. It looks almost identical across different species, and maybe your immune system is already kind of on edge from something like dust mites. That sounds like a recipe for disaster when you actually eat shellfish.
It really lines things up for a potentially strong reaction, yes.
So how does that reaction, actually happen? What goes on when someone who's already sensitized eats it again?
Well, this is what the sources call the allergic cascade.
Yeah.
The first time someone susceptible eats shellfish, their immune system might not cause symptoms, but it gets busy creating specific antibodies, IgE antibodies against that tropomyosin.
Okay.
These IgE antibodies then latch on to certain immune cells, particularly mast cells. These cells are stationed all over your body, in your skin, your gut, your airways, just waiting.
So the body's armed and ready, essentially, primed.
That's a perfect way to put it. It's primed. Now, next time that person eats shellfish, the tropomyosin protein finds those IgE antibodies sitting on the mast cells and binds to them.
Like a key fitting into a lock.
Exactly like that. And that binding acts as the trigger. It signals the mast cells to just, well, degranulate, to explosively release all the chemicals they've got stored inside.
Chemicals like histamine.
Histamine is the big one, yeah. But also others, like leukotrienes, prostaglandins, a whole cocktail of potent stuff.
And those chemicals cause the allergy symptoms we see.
Absolutely. Histamine causes the itching, the hives, the swelling. The other chemicals can constrict airways, making it hard to breathe, cause nausea, vomiting, stomach cramps.
And in the worst cases,
These chemicals can cause blood vessels to leak, blood pressure to drop, leading to dizziness, fainting, shock. The whole system can be affected.
and when that happens really fast and widespread, that's anaphylaxis, right?
That's anaphylaxis. It's the most severe, potentially life-threatening outcome. Multiple body systems are involved. It can escalate incredibly quickly, compromising breathing or circulation.
Which is why immediate action is crucial.
Absolutely critical.
Yeah.
The sources stress this. Anaphylaxis needs immediate epinephrine because it can turn fatal within minutes if you don't treat it.
It's just incredible how a protein that's so common, so fundamental, can provoke such a violent internal response. We've talked about the cascade, the protein stability, the cross-reactivity. But why shellfish specifically? Why is this the top adult food allergy, often so severe, often lifelong? What makes it different from, say, the tropomyosin in chicken or beef?
That really is the million-dollar question, isn't it? And the sources suggest it's that combination of factors we've been discussing, hitting a sort of perfect storm. The stability is key. Shellfish tropomyosin just seems to be exceptionally resistant compared to its counterpart in, say, mammals or birds.
So more of the dangerous protein actually makes it to the immune system intact from shellfish.
Yeah.
The delivery is more effective in a bad way.
That seems to be a big part of it, yeah. Then you have that broad cross-reactivity across the whole shellfish group, which makes avoidance tricky and increases the chance of accidental exposures.
Right.
And another point the sources bring up is persistence. Unlike some childhood allergies like milk or egg, which kids often outgrow,
Yeah.
shellfish allergy, especially when it starts in adulthood, tends to stick around for life.
So it's common, severe, and usually permanent if you develop it later.
That's the general picture, yes.
Yeah.
And the severity aspect is really emphasized. We're not just talking about eating a big plate of shrimp. The sources point out that for highly sensitive people, even minuscule amounts.
Like cross-contact from using the same cutting board.
Exactly. Or even inhaling steam or particles from cooking shellfish. That can be enough to trigger a serious reaction.
Wow. Those hidden exposures must make things really difficult.
Extremely difficult.
And speaking of hidden things, the sources also clear up that old myth about iodine, right? It's not about iodine.
Absolutely not. That's a really important clarification they make. Shellfish allergy is definitively caused by the protein tropomyosin, not the mineral iodine.
So someone with a shellfish allergy generally doesn't need to worry about, like, medical contrast dyes that contain iodine.
Generally, no, unless they happen to have a completely separate, unrelated sensitivity to iodine itself, which is quite rare. The shellfish protein allergy and iodine are different issues.
Good to know. Okay, so given there's no, like, cure for this immune mix-up, what's the bottom line for managing it, according to the sources?
Avoidance. Strict, meticulous avoidance is the absolute cornerstone. Meaning reading every single food label every time, asking detailed questions in restaurants about ingredients and preparation methods to avoid cross-contact. Basically, avoiding all types of shellfish crustaceans and mollusks.
And if you were diagnosed, carrying epinephrine is essential.
Non-negotiable. The sources are unanimous on this. An epinephrine auto-injector, an EpiPen or similar device, is the first-line treatment for any severe reaction.
Like trouble breathing, throat swelling, dizziness.
Any of those signs, yes. Use the epinephrine immediately, right then and there, and then call for emergency medical help or go to the ER. Antihistamines might help with mild hives or itching, but they cannot stop anaphylaxis. They are not a substitute for epinephrine in a severe reaction.
So vigilance, communication, label reading, and always having that epinephrine ready. Those are the keys.
Those are the absolute must-dos for safety.
Okay. As we kind of pull this all together, what's the one thing from digging into these sources on shellfish allergies that really stands out to you?
For me, I think it's just how clearly it shows this specific vulnerability linked to one particular protein, tropomyosin. You have its stability, its similarity across species, meeting an immune system that's maybe primed or just makes a mistake, and the results can be, well, catastrophic. It's such a stark example of how these tiny molecular details can have massive health consequences.
Yeah, you really see why it's so common, why it sticks around, why it needs such careful management. Understanding that stable protein and the immune response really explains a lot. It underlines the need for that constant awareness and preparedness.
Definitely showcases the sheer complexity of how our bodies interact with what we consume.
Absolutely. So here's a final thought for you to chew on after this deep dive. We know shellfish tropomyosin is a problem because it's stable and it triggers cross-reactivity. But tropomyosin itself is everywhere, right? It's a basic muscle protein in us, in chicken, in fish we eat without issue. So what is it about the exact structure or maybe how it's presented in shellfish that makes it uniquely able to set off such a severe, sometimes deadly immune reaction compared to functionally similar proteins from other sources? What are those really subtle molecular differences we still need to fully understand about how proteins talk to our immune system?